So, hello everyone. Yasas, salam alaikum, salute, hola, namaste, salam, greetings Swiss colleagues. It's 3 p.m. here in the island of Crete, 12 o'clock Greenwich Mean Time, 12 o'clock Coordinated Universal Time. I'm John Damilakis. Happy IMPW, everyone. Today is the first day of the Medical Physics Week, and I'll use a real-time voting to know the geographical distribution of our audience. So I'll stop sharing my screen and I'll share it again. I think this is how it works. So I guess you see you can see my screen. Again, please go to menti.com and use the code 154653339. You can use your PC, tablet, or cell phone and submit your vote. So please pin on the image. Do not drag the blue spot, just pin on your country. So using your mouse or finger, click, pin on your country, and the blue spot will move to the right place. Don't move the blue spot, just click on your country. And fine, it works. And we can see this is a day and night world map. It appears that we have many colleagues from Europe. The majority is from Europe. So I leave it for a few minutes, but in the meantime, I will introduce our first speaker. Yeah, okay, it's daytime now in Europe. So, okay, I'll leave it and I'll show you the map later again. Fine, so I'll go back to my previous slides. Okay, and the topic today is monochromatic X-rays, a new source with potential to replace century-old technology. This is a great topic. And the first speaker is Dr. Madan Rehani. As you all know, Madan is the president of the IOMP. He's director, Global Outreach for Radiation Protection at the Massachusetts General Hospital, Boston. He was a radiation safety specialist at the International Atomic Energy Agency for 11 years. And prior to that, professor and head of medical physics at the All India Institute of Medical Sciences, New Delhi, India. Dr. Rehani is a member of the ICRP. Madan, the stage is yours. I'll unshare my screen, stop sharing. And could you please try to share your screens, your screen? Okay.
Thank you, John. Thank you very much for the kind words. Thanks to all the participants from different parts of the world. Good morning, good afternoon, good evening, as the case may be. And very happy International Day of Medical Physics. We all have dreams, and when it comes to patient radiation protection, all of us have been either teaching or have been taught that if one does the justification and optimization, then the patient safety is achieved. Although it's applicable to other situations, but I'm focusing on patient safety. So that is what we have always been taught, and that is what we have always taught others. But imagine a situation when you have done the justification to the best possible extent available today, and you have done the optimization to the best possible extent available today, then what? So that may be a dream to achieve, but the fact is that in my hospital where I work now, we have a situation of having done these. We have the best possible system for justification, clinical decision support. We are world leaders in that for the last 16, 17 years. We have every week monitoring and comparing with national reference levels. And still we find so many patients who are more than 100 millisievert. Every single day, 3 to 5 patients, and globally every single day, more than 3,000 patients. So I don't want to spend today's webinar on that issue because in the last year itself, we have more than half a dozen publications. The point which I am making is that we have reached the limit of using the justification and optimization, and still we find that we have not made the patient safe. And it is there that we need other paths. So it is not only the path which we have been trying to practice. So if we have to reach the mountain, there have to be other paths. And today's webinar is that one of that is the monochromatic X-rays. So there are many technological possibilities, and today's webinar we will focus on the monochromatic X-rays. I'm sure all of you know how Ranjan discovered X-rays with the Crookes tubes in 1895. After that, the Crookes tube was replaced by Coolidge tube, which is hot cathode instead of the cold cathode tube. And this is what the Crookes tube looked like. And this is the Coolidge tube, which we have today. Also, there have been a lot of development with the generators. The electronic technology has moved to switch mode power. With that, it's better control on the quality. And so image quality is much better with the generator system also. But typically only 1% of the energy generated is emitted as X-rays. So we are losing a lot of the energy, and that is remaining is going as heat. And there have been advances in rotating anode and heat dissipation mechanisms. The typical temperature, I am sure most of you know, reaches as much as 2,500 degrees Celsius at the focal spot, and overall anode 1,000 degrees. And for radiation purpose, what we are using is the Brahms-Starling effect. So this is essentially what we are getting from the X-ray tube. The lower energy part is able to be removed by using filters, but we have to live with this continuous spectrum, which has slight emissions of the characteristic X-rays. I'm sure large fraction of you in the audience are medical physicists, and as physicists and medical physicists, one knows that photoelectric effect is really the best because it has Z raised to power Z raised to power 3, and Compton effect is a nuisance. So we want to have energy, single energy, and use it for creating the photoelectric effect and have the good image, because the other energies are giving unnecessary radiation dose to the patient and are spoiling the image quality. So this is well known from physics background itself that a monochromatic X-ray can give us better information. So the question today is how to get the monochromatic X-ray. There have been experiments using synchrotron, the huge synchrotron, and monochromator like the HOPG. And this monochromatic beam from these synchrotron have been used successfully by scientists for doing scientific studies like diffractometry and fluorescence analysis. So it's a question of seeing if the monochromatic X-rays generated by the synchrotron can be used in medical practice, but that is something which is not the case. So there are various possibilities. The K-edge subtraction, which has been tried with the conventional as well as with the monochromatic, but you cannot bring a you cannot bring a synchrotron in the hospital setting. If there are 20 X-ray rooms, you cannot have it in all the rooms. There have been attempts to have compact synchrotron based on the inverse Compton scattering, but there again the problem is that of the same. So monochromatic X-ray is not something very new. As way back in 1947 in the radiology journal itself, there have been publications like this. And then I'm just picking up very few of the many publications. 2002 to enable monochromatic X-ray, a new paradigm in medicine. In AJR in 2008, different virtual diffraction in crystals, laser-driven X-ray source, and clinically also using the virtual monochromatic imaging, one has shown that how the cyst in the kidney, the unnecessary enhancement which comes from the conventional system can be reduced. So the pseudo enhancement of the renal cyst becomes low if we use the pseudo monochromatic X-rays, and the overall image also is maintained. So some clinical experiments, and also on the animals, one has tried the K-edge subtraction imaging, and one is able to show this is the temporal, this is the normal, this is the temporal subtraction, this is the K-edge subtraction, that how the image quality can be better. So with this very brief background, so let us have a wish list of what we want. First thing is we want monochromatic X-rays instead of the continuous spectrum. Second thing, we do not want synchrotron based because it is not really possible on a large scale in every, if we want to implement in every X-ray room of the hospital. Third thing, we feel that it will be ideal if it can be in a typical X-ray room, so it can be made available there. Next is, suppose since it is a wish list, it can be like the conventional X-ray tubes which we are using today. It can be of that size, and that could be really. So when we are dreaming, so let us dream of the various points, and that brings to the fact that the conventional X-ray tube, despite its limitations of low efficiency and all, it has many, many plus points, and we do not want to lose those plus points. So I am listing all those plus points so that the new source should be able to have those ones. So best if it can fit into the current X-ray machine by replacing the X-ray tube so that the size-wise it remains same, and then the cost, it should not be exorbitant or should be almost equivalent to the current X-ray tube. We are able to have energy selection in the conventional X-ray tube and X-ray machines. And also we are able to have auto energy selection. So can we have those in the new development if we want to make? Still more needs the uniform X-ray field, wide field of view, X-ray flux enough for imaging thick patients. We have all sorts of patients, and the conventional X-ray tubes are able to do that. And they are being used for CT imaging, interventional fluoroscopy. And finally, lower dose we want than the current systems and better image quality. And still, finally, still, let us look at the limitation of the current day X-ray tube. They are not really good for the dense breast. So we want that if we have a monochromatic source, it should be able to take away the limitations of the current day X-ray tube. So with keeping in mind that for the last over 100 years, there has been no solution to all these wish list points. There are millions of X-ray tubes being used daily, and there has been so much R&D all these 100 years. So it's a big task. So let us see out of all these wish list points which I have listed, And it is time now, I'll pass on to the next speaker, Eric Silver, who will be dealing with this wish list. So my purpose was to create this wish list for him. Thank you.
Okay. Hello, everybody. Thanks for the opportunity for me to share our latest developments regarding monochromatic X-ray production. I'm going to share my screen now, if I can. Okay. So as some of you may know, I'm an astrophysicist by training. I've used X-ray spectroscopy and X-ray imaging techniques to study some very exotic objects in space and in the universe, black holes, supernova remnants, extragalactic nuclei, and pulsars, for example. But recently, I felt it was very important for me and some of my people I work with to use these same X-ray techniques to advance medical X-ray imaging. So I'm going to tell you about our monochromatic X-ray imaging development, which provides high quality and low dose medical imaging. Our initial application, just to let you know, is in mammography. We're addressing the #1 unmet clinical need in medical imaging, and that's satisfying our demand to be able to examine women who have dense breast tissue. There are more than 40% of women in the world with dense breast tissue. I'll show you working prototypes and demonstrate the performance. So just to put this in context, Madan showed you, and a lot of you are familiar with using medical X-ray tubes and the way X-rays are produced in those tubes. But from my point of view, this is how I came to be able to come up with these ideas. We use X-ray spectroscopy to study these objects that I mentioned to you before. And from the spectral properties, we can learn something about their gas temperatures, their densities, their ionization states, elemental abundance, and gas velocities. So for example, this is an image in X-rays of the Cassiopeia A supernova remnant made by the Chandra X-ray telescope. So you're all familiar with X-ray bremsstrahlung, which makes a continuous spectrum. And there it is. This is this continuum spectrum that we measured from the Cassiopeia supernova remnant. Characteristic line emission is superimposed on this continuous emission, as you can see here. And so now let's move to a terrestrial source, which is the conventional medical X-ray tube. You've got the cathode emitting electrons bombarding a metal target, and it makes the continuous spectrum, which is analogous to what comes from a celestial source with some characteristic line radiation on top. But we also use an additional process that takes place in the universe, and that's called X-ray fluorescence, which basically in a cosmic source is a photoionization. You can excite an atom by irradiating it with an X-ray photon. You can make, therefore, a photoelectron. You then have a vacancy in the K shell, which is filled by an electron from an outer shell. Each one of these two photons are monochromatic because of the quantized nature of the atom, and every atom has a characteristic X-ray based on their atomic structure. So here we are again, and as Madan showed you before, you start off with a bremsstrahlung spectrum. This cutoff at the low energy ends is due basically to the self-absorption in the target, but then because we want to reduce, people have wanted to reduce the total dose to the patient, you would filter it with thick filters, aluminum, rhodium in particular. We'll actually do some filtering in the low energy end and on the high energy end from the rhodium Ka. But what if we had a monochromatic X-ray source? Here you can see the same filtered spectrum. This would be probably from a tungsten target, but if we had a monochromatic line, we'd have less tissue absorption. You know that 95% of the radiation coming from this total continuum source is absorbed in the breast. Monochromatic X-ray wavelengths can be selected to optimize the breast cancer detection. It has better signal to noise, and therefore the radiation, plus the radiation dose is considerably lower. And you all are familiar with the fact that a cumulative dose would be dramatically reduced over a woman's lifetime in the 30 to 40 scans she would have. Madan alluded to the two techniques, at least one technique that has been used to make monochromatic X-rays. Well, here are two, one using X-ray fluorescence and one using the Bragg crystal. And the input source is either a continuum source made from a conventional X-ray tube or the broadband continuous spectrum made by a $100 million electron cyclotron. You can see you would get monochromatic radiation, the fluorescence emission from a flat target. You could also get a very narrow line from a Bragg crystal. However, the conventional medical X-ray tube is too weak and has a diverging output, which can't effectively be focused to generate enough X-rays to make a useful image using either of these techniques. The Bragg crystal coupled to the intense synchrotron, though, has shown the advantages of using monochromatic X-rays, but as Madan pointed out before, a synchrotron does not make a practical solution for the clinic. And mind you, using a Bragg crystal connected to either of these sources requires scanning of the sample because the beam is relatively narrow in space. So what we've developed is this new technology, and what I'm showing you here is a conical, inverted conical anode target, which is irradiated by electrons through a high voltage potential. The broadband X-rays that are emitted from the circularly symmetric primary anode are then emitted into 2π, and a good fraction of them interact with a secondary target. This secondary target is compact. The best one we have designed so far is a thin foil of a metal or any material whose characteristic X-rays represent the monochromatic X-rays that one would like to use for the imaging. Oops, sorry. Here it is. The guts of this concept are built into this shroud sitting on top of a conventional mammography machine. This is about 330 millimeters by 100 millimeters wide. This is a typical mammographic X-ray machine that one would find in a clinic. You can see it's about 1 foot wide. We have 10 issued patents on this and 7 pending with worldwide coverage. So let's look at some of the spectral characteristics. Here is a monochromatic emission from the tube using a tin compact absorber. You see the K alpha and K beta lines from the tin. The monochromaticity of this source is 96%. Here are examples of a monochromatic emission from several other compact secondary fluorescers. And here's a list of potential fluorescers one can use for low energy and high energy work. Let me show you, for example, some higher energy monochromatic lines that can be used for cardiac and even for CT. What you see here is monochromatic line around monochromatic emission about 94% monochromatic from neodymium at 38 to 40 kilovolts. And here's tungsten emission at 60 to 70 kilovolts. Spatial profile is relatively flat, and the half width corresponds to about 20 degrees. And this is what it would look like coming out, what the detector would measure. So we've used standard X-ray phantoms, which simulate breast composition and density, to demonstrate the performance and what the advantages of monochromatic X-rays will yield. So this is our first generation prototype mammography machine with the monochromatic source installed. Here's the mammographic imager. I'm sure many of you have used these from the CIRS Corporation. We use an amorphous selenium X-ray imaging detector, which is a common mammographic imager. And here is, for example, what that phantom would look like. Let's look at it in more detail. The image on the left here is made from a conventional mammographic X-ray, broadband X-ray machine. You can see the embedded step wedges with varying density, glandular densities from 100% all the way to 100% fat. You can see microcalcifications and some simulated thin lesions. We measure a signal to noise. We want to be able to compare this image. Well, let me show you first. This is an image made at monochromatic energy of 22 kilovolts, and this is an image made at 25 kilovolts for the same phantom. So how do we compare them? Well, we don't really know. We can't exactly calibrate each one, because each machine to each other, because they have different processes taking place, and the instrumentation is different. The figure of merit is the signal to noise ratio. That it removes any issues having to do with calibration. So we measure the signal to noise in this 5 millimeter square in the 100% glandular block, compared to the background material, which is 50% glandular, 50% adipose equivalent. So we measure a number that corresponds to 403. It's not important to know how we got that, but it is 403. We could talk about that later if you're interested. Here, we had measured 500. Here, we measured 460. The important thing is that for the conventional machine delivered 1.26 milligrams of dose to the phantom. The mammographic imager at 22 kilovolts delivered 0.27 milligrams and 0.23 milligrams at 25 kilovolts. If you want to compare them directly from the standpoint, if we had equal signal to noise, 403 for both, this dose of 0.27 would drop to 0.175, and this 0.23 to 0.177, factors of 7 times lower. Now, this is a very, very interesting result with important ramifications. We go to the other extreme. We've made a 9 centimeter thick phantom and measured images with the conventional broadband machine and the conventional, and our unconventional monochromatic system. Here we used a 3 by 3 millimeter square only because we had a crack in the top phantom, so we just made it a little bit smaller. We'll talk about that later. But for the conventional machine, to give a signal to noise corresponding, in this case, to 138, it had to raise the dose to 2.75 milligram. With only 0.65 milligram of dose, we got a signal to noise that's more than twice the value. So what does this tell us? If the conventional machine had to achieve the same signal to noise, it would have had to raise its dose to 14 milligram. Think about it a different way. The monochromatic signal to noise would be 749 as opposed to 364 if we operated at 2.75. If the conventional machine operated to equal the performance of the 749, then the conventional machine would have had to raise its dose to 81 milligram. Obviously, these numbers are out of the question for use in the clinic. So let's put it in perhaps more context. If we measured the signal to noise in the same 5 by 5 millimeter area that we did for the 4.5 centimeter breast, we would have had a comparable signal to noise in the 9 centimeter image as we did for 4.5 centimeters. So at 25 kilovolt monochromatic energy, the system has equivalent signal to noise over the range of 4.5 to 9 centimeter, but the dose is significantly less. For an equal signal to noise of 9 centimeter breast thickness to the 4.5, its dose would be 0.46, 2 to 3 times less than the dose delivered by a conventional machine at 4.5 centimeters. So this begs the question. This could introduce a paradigm change in a woman's mammographic experience, because if you can achieve the same signal to noise capabilities on very thick breasts, why compress them at all? Here are some examples of looking at more difficult, very thin lesions, ranging in thickness from 1 millimeter to 200 microns. And these are the signal to noise values. For the 1/4 millimeter and 0.5 millimeter thick lesions, the monochromatic dose is 6.5 times lower than the conventional dose. And to really challenge the two systems, we looked at these same very thin lesions in a 7 centimeter thick compressed breast, and we're 4 to 5 times lower in dose, even all the way down to, you can even see, very difficult for the broadband machine to see the 200 micron thick lesion. So let's look at the spatial resolution by looking at microcalcifications. From that same phantom, I show you here 3 series of 400 microns to 230 micron diameter microcalcifications. And these are the image profiles along these yellow lines, showing that this is what the conventional machine measures as a full width half max for the 400 micron, and here 397 for the 230, excuse me, this is the 231. This is the comparable one for monochromatic radiation. Quite comparable, but the dose here is 0.27 milligray compared to the 1.26. This is one of my favorite slides. This shows the imaging of glass spheres, which are a little bit more difficult to see than calcium because the atomic number of the glass is lower than calcium's atomic number. But these range in size from 330 microns all the way down to 170 microns, but the dose for the mono image is 0.55 compared to 3.62 for the broadband source. Similar comparisons for the 9 centimeter thick breast from the broadband to the mono. Again, 2.75 milligray to 0.65. So we've done a little bit of contrast enhanced imaging. We're doing a little bit more now, but this shows the strength of doing contrast enhancement with monochromatic radiation. Here you see that same phantom blown up, expanded a little bit, and these are Oxalon 350 iodine contrast agent dots. You can see through the histogram of the following this yellow line, these are the signal to noise values at a dose of 0.057. Now, in most contrast enhancements used to date with conventional machines, 2 measurements are made. One by lowering the endpoint energy of the broadband spectrum so that you don't get absorbed by the absorption edge of the iodine, and then you raise it above it so you can improve the contrast. Well, here you get wonderful signal to noise in only a single measurement. If, for example, you wanted to perhaps remove any kind of fluctuations that you see here in the tissue, just take the image without the contrast and subtract it. Here, of course, you see now the fluctuations are going away, but when you always subtract 2 images, you're going to increase the noise by square root of 2, and you're going to reduce the signal to noise by a square root of 2. One can also do dual energy contrast enhancement, which we are beginning to do, but to do that best, you need an imaging detector whose quantum efficiency does not drop at higher energies. For example, if we wanted to go up to 35 to 40 kilovolts to do contrast enhancement with a higher energy X-ray, we would need an imaging detector that has a higher quantum efficiency than the 40 or 50% that the amorphous selenium detector does. But this is quite interesting all by itself. So a lot of this information and the data that I've shown you is now published in our first medical physics publication, volume 48, which came out in March. And we are now developing a next generation instrument that will have more power, more X-ray intensity that will allow us to reduce the exposure times to make them comparable at all thicknesses to the conventional X-ray broadband system. So let's go back and look at Madan's wish list. Do we satisfy any of them? Well, we satisfy number one, the monochromatic source, and it's surely not of synchrotron size, and it definitely fits within a usual X-ray room, and it does fit within a standard X-ray machine. I didn't show it sitting standard within the, it's on top of it in our first generation, but our second generation, we're turning that vertical X-ray monochromatic source horizontally, and we'll hide it inside the gantry. The cost will not be any more than a conventional current X-ray tube. All of the components from the standpoint of materials and electronics are quite similar. We surely are able to select the energy. I didn't mention that before. If you go back and look at the picture, that compact source made out of the thin foil is at atmospheric pressure. Those X-rays, that broadband X-rays that come off the primary, pass through a beryllium cone, a beryllium cylinder. That beryllium cylinder serves to be the vacuum seal and the window. So we change that compact secondary fluorescer anytime we want. Right now, it takes 5 to 6 minutes to do it by hand, and our X-ray, our auto selectable one, is under development. We have a relatively uniform and definitely wide field of view, and I've shown you the beginnings of our work to increase the intensity so that we can see thick patients and do CT in the future. The improved signal to noise allows us to do two things. First of all, for the same signal to noise, the dose is significantly lower. Well, if you wanted to use the same dose, your signal to noise is going to go up factors of 3 to 5. That increased signal to noise will make it possible for us to detect or image more effectively and hopefully conclusively women who have dense breast tissue. We surely have demonstrated a lower dose, and our image quality is better. So thank you very much.
Thank you. Thank you. Moderators usually, let me switch on my video. Okay. So moderators usually introduce speakers before their presentation. I didn't want to interrupt the flow, but it is never too late. So I can share my screen, and okay, I hope you can see Eric's short CV. So Eric has spent 21 years as a senior astrophysicist at the Harvard-Smithsonian Center for Astrophysics. He received his bachelor in physics from MIT and PhD in astrophysics from Columbia University. Eric was a recipient of an NIH Challenge Grant and the George Bush Fellowship for New Medical Applications, and has 16 patents to his credit. Okay, and maybe it is also an opportunity to have a look again before we getting into discussion. We have many questions from the audience. Let's have a look again at the map. So, okay, the majority is from Europe, but it is obvious from also from the chat that we have many colleagues from Asia and other parts of the world. So in total, 571 participants right now. Okay, so we have some questions from Alan Calvert. What is the effective focal spot dimension, and what is the dose rate?
Okay, I heard the first question. You'll have to repeat the second, but first, the effective focal spot is 2.5 to 3 millimeters, keeping in mind that the source to detector distance is 760 millimeters. And what was the second question?
About the dose rate. Could you please give us a
okay.
number? Yeah.
Yeah. What I can tell you is that for the 4.5 centimeter compressed phantom measurements that I showed you today, we used our first generation system uses an input power of 1.6 kilowatts with an 80 kilovolt high voltage between the negative cathode and the grounded anode, and it takes 9 seconds to make the image of the 4.5 centimeter compressed breast, and significantly longer, about 70 seconds, to make it for the 9 centimeter compressed breast. But if we were to go back and look at that last slide that I did show you, we're increasing the intensity by a minimum of a factor of 10, and that will reduce the exposure time to less than a second for the 4.5 centimeter and to about 6 to 7 centimeters for the 9 centimeter thick breasts. But mind you, I had on that slide just to show you that those numbers correspond to meeting a signal to noise value that is accepted as the accepted figure of merit for good imaging. For the conventional machine, it would take about also 7.5 centimeters to achieve the same signal to noise as we will with our advanced system. But the conventional dose would be at 14 milligray, where ours will be 0.6.
There are some questions about the metrics. You use the SNR. Why only SNR as a figure of merit? Why not resolution?
Well,
using
using
a contrast detailed phantom.
Well, the comparisons we made in spatial resolution were made on microcalcifications from the same phantom, and we compared the same microcalcification diameters from one machine to the next.
There are a few questions about higher voltages because your presentation was focused on mammography and lower energies.
Yes.
So could you please comment?
Yes.
Are there any?
Well, I'll answer that question. The slide the spectrum that I showed where we produce the tungsten emission lines, that was made with a high voltage of 110 kilovolts, and we would expect to be able to, we go up to 160 kilovolts with our system and with our next generation system. We will evaluate what's required for CT. There are, of course, I'm well aware of the fact that conventional CT machines go up to 200 kilovolts. But yes, just to tell you that to make that tungsten, it was most effective, of course, to double the high voltage. But we went up to 110 kilovolts for that one. We'll get more emission if we went up to 160.
Thank you. Monochromatic phantom images look non-uniform compared to conventional images. What is your comment on this?
Well, okay. I want to point out that what I'm comparing here is raw data from the conventional machine and raw data from the monochromatic machine. That was the best way and really the only way to compare apples to apples. Conventional machines and radiologists typically look at images that come from machines where the data has been processed, either through by many different ways. Many of these are proprietary to the companies, and we're surely not, cannot make ourselves those techniques available to us. To make the comparison, we'd have to use the same techniques. And so all we have done is done a very straightforward flat field correction from taking that broadband, that broad spatial images that I showed you in the two orthogonal directions and just flattened it that way. I'm sure that if we were to use some fancier processing, there would not be much difference.
We have some questions about exposure time. So in the examples, the exposure time is too long.
That is correct.
So there is always a possibility for motion artifacts. So people.
That's a very good question. Well, first of all, this instrument has never been taken into the clinic. We hope to take it into the clinic very shortly to do our first studies on women. Right now, we recognize that a 4.5 centimeter compressed breast or compressed phantom equivalent takes 9 centimeters to make an image, and longer for a much thicker phantom. Now, obviously, there may be artifacts due to motion, either. However, if one thinks about how a tomosynthesis scan today is done, conventional machines tomosynthesis scan range in total times from around 6 seconds to 25 seconds, depending on which manufacturer you use. The total dose is divided amongst the number of angular positions that the individual images are taken. So if we deliver a dose of 0.2 milligray in 10 seconds, we can deliver 0.2, we'll deliver the same dose over 10 seconds. That 10 seconds corresponds to the same amount of time, if not less than the total tomosynthesis scan. So we can use the same types of techniques used to reduce image blur if necessary. They will become less important as our exposure time gets shorter.
But I think you have already mentioned that the current results are from 1.6 kilowatt power, and if you increase the power by 10 times, so this will reduce the scanning time also nearly 10 times. So
yes, that is correct. That is correct.
This is an experimental system we have at the moment, and this is at a very, very low power of 1.6 kilowatt.
That's right.
Definitely. There are several questions about specific applications. So people ask if there is a potential to use your technique in breast computed tomography, in radiation therapy, for blood irradiator modalities.
Okay.
I think I'll give a short answer to this. The current CT machines go up to 100 kilowatt, at least 50 to 100. So imagine from 1.6 to that. So the flux as well as the energy, both will be possible. So I think the rest, I think Eric, you can add more on that.
Okay, well, I've spoken to several people about breast CT. They were telling me that they would love to have energy somewhere around. They use KVPs for breast CT around 60 kilovolts. Obviously, if you have a KVP of 60 kilovolts, your average energy is going to be somewhat significantly less. I've showed you now we can provide a monochromatic energy at 60 kilovolts. We can from 30 to 60 kilovolts would be perfect for breast CT and for doing iodine contrast at depending on whether you're looking through the heart, whether you're looking through the breast. That will determine the eventual choice for the high energy monochromatic line. But all of those applications are, as we say in America, in the wheelhouse.
Our colleague Miguel de la Guardia from Texas asks, would like to see some pediatric applications, he says, for this technology. Those saving measures with improved signal to noise ratio are a must for pediatric imaging.
I'm sorry, I missed the beginning of that, John.
Yeah, he would like to see some pediatric applications for this technology.
Pediatric, did you say?
Pediatric
applications.
Yes. Those saving measures with improved signal to noise ratio are a must for a pediatric imaging. It's very important for pediatric imaging.
I agree, and we should work together. We need.
Yeah, I mean, in principle, it should be and it will be possible, because in pediatric, it is a question of smaller subjects with a little lower energy, and all those energies are possible in the table which we presented a few minutes ago. And the intensity of the X-ray also is possible. So it's doable. So it's only a question of going further with the design.
And then there is another question regarding reconstruction. Let me have a look. Yeah, any difference compared to conventional mammography unit? Differences?
In the construction of the source or tomographic reconstruction? What was the
Tomographic.
question?
I understand the question is about tomographic reconstruction.
I don't see why. We haven't done much tomographic reconstruction. That prototype that I showed you we just recently added the scanning capability. As I said, it was a used machine, it was not capable of that. So we're beginning to do tomographic reconstruction, but I don't see why. We cover the same field of view over the sample, and we scan the same amount of angular space. So
yeah, but I think his point was
tomographic techniques. I've done
his point was on the reconstruction because of multiple energy and single energy. So it's a question of doing the and it will be rather easier in our case.
Also, there are a couple of questions about the detector technology you use. The people ask for some details.
Okay. Well, I'm using an amorphous selenium imager. It's about 3,500 by 2,500 pixels. Each one is 85 micron pixels. It's made by Analogic Canada, which supplies a good fraction of the mammographic imagers to the commercial manufacturers. I would love, of course, to have a photon counting detector, and I would expect that when we do CT, we'll switch to a smaller size, but do photon counting. If someone in the audience has a photon counting detector with this field of view that we have, let me know. But I've been in the field a long time and I don't see one that size yet.
What are the limitations to the upper limit of power that could be applied to lower the exposure times? Is 10 times near the limit?
Well, we've discussed this before. The nice thing about this design is that the stationary anode is large. So the first stage where the electrons bombard the anode are dispersed over a large area. So the power density is low compared to what you have in a rotating anode. So the instantaneous power and the continuous power density is the same, whereas in a conventional anode, the reason you have to spin it is because the instantaneous power is 15 or 20 times higher. So there's no reason to spin this because we're already dissipating the heat, and now we're using it as our first stage. So as I was just discussing with a colleague doing CT the other day, 50 kilowatts and 100 kilowatt tubes are used from CT. Right now, we have a power density of about 1 kilowatt. Our second generation source will have a power density of around 1.5 kilowatts per square centimeter. And if you went up to 50 kilovolts, it would probably be 7.5, and that's still very low compared to what you have in conventional sources.
And how fast does the system heats is a question. But
I'm
the
sorry.
heating.
What was the question?
How fast does the system heat?
Heat?
Heat. It's about heating.
Temperature.
Temperature.
The temperature. Oh, yes. Well, the nice thing about this stationary anode running at ground potential, it's very easily and straightforwardly water cooled.
Also, there are.
So I was going to say, we keep the temperature now at the 1.6 kilowatts at around 20 degrees C, 20 to 30 degrees C. And the next one, given the fact that the power density is not going to be that much different, it may go up another 15, 20 degrees.
Also, there are a few questions about the tube design and physics. What is the, could you please give us some more details about the physics behind this monochromatic beam production?
Sure. I mean, the physics, everybody, I'm sure, in the audience. Thank you, Madan. Or is that John? I don't know who's doing that.
I am projecting, yeah.
Okay, thanks. You're all familiar with the physics. We have not invented any physics. We've just applied it differently. We're using a toroidal cathode. Reference to negative, in this case, 80 kilovolts. The electrons are then focused through some specially designed electron optics, and they bombard an inversely inside of a cone. That's a combination of tungsten gold on the coating on a large copper mass, okay? Then those broadband X-rays go out, and a decent fraction of them, depending on the solid angle. Oh, you're doing that. Okay, thank you. Okay. Irradiate this secondary cone. Now, I pointed out, I mentioned to you before, Madan, show them the beryllium window, the cone, the beryllium cylinder. Okay. I can share this. There, okay. That is the vacuum seal to the inside tube, so the electrons hit the primary target unimpeded. They pass through this beryllium window, remember atomic number 4, highly transparent, and they irradiate this secondary target. And the secondary target is a single or double 35 to 40 micron foil of the material whose X-rays you want to produce through X-ray fluorescence. The atomic physics is atomic physics. Those photons, as I showed in one of my slides, excite or ionize an electron in the K shell. That vacancy is filled by an electron in an outer shell, producing the K X-rays from this target. Now, the interesting thing to note is that the total area, surface area, is what contributes to the intensity of the monochromatic source. It turns out that the average, weighted average of this X-ray intensity, weighted by the surface area, determines quite accurately the effective focal diameter. So we can make it longer by keeping the base diameter fixed. We can increase the entire emitting area without changing the focal plane, the focal spot.
Thank you, Eric. Last question. We don't really have much time, but one last question. Does the tube have significant leakage radiation in comparison to conventional X-ray tubes? Have you measured the leakage radiation?
Yes. Well, we use tungsten on the outside plus the appropriate layer of lead. So we've measured that. And we have recently measured the X-ray scatter coming out of it, so that to make sure that we are well within the safety requirements of the medical technologists in the hospital, and we're down by a factor of 50 to 100. So yes, it's as safe as, if not safer than any other tube.
Thank you, Eric and Madan. We have received many thank you messages for this very, very interesting webinar. And please let me remind you that tomorrow the webinar is on artificial intelligence. same time. So if you are interested in AI and don't know how to start, this is the webinar for you. And then on Wednesday, patient radiation protection, how the agency IAEA and WHO are contributing. And on Thursday, does contact shielding improve patient safety? So the speaker, Paddy Kerrigan, will try to answer this important question. And last webinar on Friday on the management of unintended and accidental exposures by Dr. Colin Martin. So once again, I would like to thank the speakers for this very, very interesting presentation and the participants for their active participation. Many thanks. See you tomorrow.